Welcome back to Codex. Our speaker today is Hau-Tieng Wu, who's an associate professor in both the Department of Mathematics and the Department of Statistical Science at Duke. Professor Wu received his MD from National Yang-Ming University in 2003, and then his PhD in mathematics from Princeton in 2011. He's well known for developing tools in applied harmonic analysis and machine learning to perform new types of medical signal analysis. Today, he'll tell us about manifold learning. Take it away, Hau-Tieng.
Okay, thank you, Dustin, for your introduction and kind introduction and the invitation. It's my great pleasure to share some of my recent works with you. And so let's start. So the motivating example is the liver transplant surgery. So when do we need it? Usually when we have liver failure, many reasons. And what happens is the patient will be sent to the operation room, and the surgeons will open your abdomen, remove your old liver, and implant a new one. And then after the surgery, usually you can survive for some time. As you can imagine, your abdomen will be opened, your liver will be removed, so it will generate a significant hemodynamic instability during the surgery. So usually we need a variety of hemodynamic monitors so that physicians know what's going on during the surgery, and so that they can keep patients alive. The main example I will show you is one of that many monitors from very invasive one to less invasive one. Like arterial blood pressure is the signal recorded from inside your radial artery, usually, and you put a catheter inside it and record a signal, and which is considered minimally invasive one, still invasive. And during different phases of the surgery, you can see different morphologies of the waveform. And too bad I cannot use my pointer so that I cannot indicate which part is which. That is still I cannot figure out. Very annoying. I don't know what's wrong with it. Usually from those signals, physicians can calculate several indices to monitor the hemodynamics. But usually those information was used mainly to monitor the hemodynamic trend during the operation. Okay, like what's really going on. But can it be used to predict the outcome or get more information about your health status that is somehow still relatively open? So for example, it is we cannot use currently we cannot use the existing indices like what I showed on the left lower part to predict the outcome of the liver transplant surgery. So somehow it is a huge waste of 10+ hours waveform. What can we do to get the useful information? So the question is, if we could properly quantify the hemodynamic structure, can we better understand the surgery or better assess the clinical outcome? That will be our hope and the question. So first thing first, like arterial blood pressure is non-stationary. It's non-stationary. So what it is doing is the following. Your heart may beat once, and your heartbeat will behave like an impulse to the whole system. To what system? Your cardiovascular system, which is shown on the right-hand side. Suddenly, my arrow appears, and I hope you can see my cursor.
Yes.
Wonderful. So you can see the your cardiovascular system, which you can view it as a drum, or you can view it as an echoing chamber. And so that when your heart beats, which will squeeze a shock of blood into your cardiovascular system, and your cardiovascular system will react to that shock. So you see some response, or sometimes we call it impulse response. And your heart will beat periodically. Each time when it beats, it will send an impulse to the cardiovascular system, and you get an impulse response, and you continue to do it. Okay, so your heart is beating, and you will get this kind of repeated responses. Now, if your liver, wait, that's weird. What? Okay, fine. So ideally, I should have some, okay, I missed something. So your liver is removed, for example, in the middle phase, where your liver has been removed. And this is when the new liver is implanted. Then you will see that the morphology, the responses, changes from time to time. So in addition to the global difference from phase to phase, you see that inside each phase, you can see some small variabilities. So the hypothesis is, by reading this, we see that, hey, the morphology of impulse responses and the associated variability could reflect the properties of the cardiovascular system. Something very much like you have like a drum, and you click it, right? And if you put if you change the structure of the drum and you click it, then you hear different sounds. So that will be something we are interested to quantify, and we suspect that such difference, such variability, will give us the information we are interested in. So we have been motivated by such a physiological fact to model to propose a new mathematical modeling of non-stationary time series. So again, you have impulse, continuous impulses, and you get several impulse responses. And the physiological fact is that although, as you saw before, there is a variability, but it does not really go crazy or random. For example, your blood pressure is always consist of systolic phase and diastolic phase. So for one cycle, it cannot be just like a random Gaussian noise. So there is a structure inside. So what can we do? We proposed to parameterize all those impulse responses by a low dimensional smooth manifold in the following way. So you have manifold, and this manifold will describe a relationship in between different impulse responses. So you will see for similar responses, they are clustered in one location, and for something very different, they will be clustered in another location. So somehow that will be the model for the impulse for the arterial blood pressure. So the challenge, overall challenge related to this problem and related to the diffusion-based learning. Okay, now I cannot see my cursor. So it's weird. I don't know when I can see my cursor. The challenge is we record this arterial blood pressure signal during the operation room, and we truncate the long time, like 8 hours signal into pieces. Each piece represents one impulse response, and we get a bunch of different impulse responses, like S1 up to Sn on the left-hand side, which we assume to be located on a manifold. And our goal is to recover the latent manifold and the dynamics. And there are several challenges toward this goal. For example, how to model the system, how to recover the latent space, what about if the database is big and noisy, particularly when noise is colored and heterogeneous, heteroscedastic, and how to obtain useful clinical information, etc. And well, I will not talk about 1, 2, 4, 5. I will focus on 3 today, and so that and certainly show you some results in this direction. So that is the overall goal of today's talk. So the first part is diffusion geometry approach to handle this non-stationary time series, and we'll tell you a new algorithm which is scalable and robust. And the third part will be kernel random matrix and the bandwidth. But when I prepared the slides, I realized that maybe I was too ambitious when I prepared the abstract for Gaussian. So I think the third part will be skipped. But I also prepared the slides, so in case we have time, we can quickly go over there. So let's have a quick recall of diffusion geometry-based approach. So in general, we have n points in high-dimensional space, RP. And usually we construct an affinity graph. Okay, and the affinity graph can be constructed using different approaches. For example, you can connect any pairs of any pairs of 2 points, which gives you a complete graph, or you use kernel scheme to connect only neighboring neighbors points, or you construct using epsilon bow scheme to connect 2 points when their distance is less than epsilon. There are some basic ways to do it to get affinity graph. Then once you have the graph, you need to assign an affinity. And the affinity between xi and xj usually is defined using this kernel function. And the kernel function, for example, here is a Gaussian function, Gaussian type kernel function. You have some metric which you like in between xi and xj squared divided by epsilon, which is a bandwidth. Okay, so you can choose many other different kernels. You can choose different matrices. You can choose different epsilon. Then you can play different games, blah blah blah. So which gives you many different kinds of algorithms. And but usually that is a kind of the overall framework of the algorithm. And the matrix design will not be discussed today, which is related for the liver transplant problem. That is related to the latent space recovery structure, which we will not touch. And for the bandwidth selection, that is related to the kernel random matrix algorithm, which we will also not touch today, maybe later. Yeah. Okay, once you have affinity graph, what you do is you construct an n by n affinity matrix as usual, and you construct an n by n degree matrix, which is a diagonal matrix where each diagonal entry is the summation of the row entries. And you construct a transition matrix, inverse type. Okay, once you get the transition matrix, as you can imagine, we now have a random walk on the data set, and which gives you the random walk or diffusion on the graph. So what you can do is you can run eigendecomposition, and you get the right eigenvectors and the left eigenvectors. And here is a teeny tiny small details you have to pay attention. That is, if you use a kernel scheme to establish the graph, then the W matrix may not be diagonalizable. So you may want to be careful when you use kernel. You may want to do symmetrization or do some small tricks to guarantee the eigendecomposition. But usually this is not too terrible. And then what you do is, for example, in the diffusion map field, diffusion map algorithm, what you do is you take the eigenvalues and eigenvectors. And for example, I still cannot use my cursor. So still real, no cursor. Okay, so on the right-hand side, you can see the phi t of I, phi t of I. What we do is we map the i's point, xi, into a q-dimensional space by using the i's entry of the eigenvectors multiplied by the eigenvalues, associated eigenvalues raised to power t, where t is the diffusion time. Okay, so you get, you convert a set of point clouds, into another set of point clouds, but now it's in two-dimensional Euclidean space. And this is the overall algorithm, which is actually very simple. You can code it in MATLAB using just maybe 5-10 lines, very simple. But turns out it is quite useful. It is the original version of this kind of kernel approach was proposed back in 2000. For example, locally linear embedding or ISOMAP, and then in 2003, Belkin and Niobe proposed the eigenmap, and then 2006 there was this diffusion map, and then there was kind of blooming several different algorithms, and they are mostly used to visualize high-dimensional data and the dimension reduction, even recover nonlinear geometry. And there's a bunch of literature which is far from exhaustive, but I just want to show you some existing results, mainly for theoretical support to show okay what's really going on, and almost everything is can be traced back to the spectral embedding theory of over the manifold setup. If you have a manifold, and if you don't have manifold, there will be some other work, theoretical work. Even locally linear embedding, there are several open problems here. Like even locally linear embedding, the theoretical result was established just in the past 2 years about the convergence and how it is related to Laplace Beltrami operator and so on. So if you're interested, you can look at some annals of statistics paper. Okay, so let's have a basic understanding of the algorithm and see how it works. So we consider manifold setup. You can consider more general stuffs. For example, recently there are some group of people starting to consider RHK as consider some matrix spaces with some singularities and so on, but we won't go that far. So suppose M is a manifold, okay, d-dimensional manifold, close and connected, very simple. We don't consider too crazy manifolds. And you have a random vector x, and you sample points xi from a manifold, which we assume is isometrically embedded in some Euclidean space. Okay, and we assume that the density function associated with x, px, has some regularity, and its inf is positive, which means that you can sample everywhere. There won't be any single place that you cannot sample. Okay, and now you sample n points IID from x. Now we can take those n points as our point cloud, and you construct an affinity. And the affinity we consider here is a specific one, which is a kernel random matrix, as we saw before, k epsilon. But we do some normalization, which is usually we call alpha normalization, which was proposed in 2006. The purpose is to remove the impact of the density function so that you can see something intrinsic instead of something extrinsic inherited from the density function, the random vector itself. So you have q epsilon xi and the q epsilon xj. And you can see that q epsilon x can be understood as the density function estimation, kernel density estimation. Although you may want to do some further normalization, like 1 over any front, but all those constants will be canceled out in the end. Okay, so the first result was published last year in 2012, 21 in ARCHA is this L-infinity spectral convergence result. Because remember, in diffusion map and the eigenmap and other relevant algorithms, we care a lot about the using eigenvectors to represent the data. And the eigenvectors, if it is if the data set is sampled from a manifold, then we expect that it will give us something useful. And for a long time, back in 2003, 2006, people started to realize that, hey, it will be Laplace spectrometry operator of the manifold that the algorithm it will give us. Yeah, but at that moment, people could only prove pointwise convergence. And then in 2007, 2008, Belkin, Belkin, he started to prove the spectral convergence. But at that moment, there was no rate, and the convergence was mainly on L2 sense. And then starting from 2017, 2018, we started to work on this problem and try to push the result from L2 to L-infinity and try to give the rate. And so that we can see that all the eigenvectors of the Graph-Laplacian will actually converge to the eigenfunctions of the Laplace spectrometry operator, and we guarantee that the L-infinity norm will be bounded and converge to 0. And that's what we have. That's what we provided in this ARCHA paper. So you can see. I will not go into details 9 by 9, but that is essentially what the theory tells you. And there is another team in Minnesota and Wisconsin work on similar problem, and they also have similar results later. Okay, and with this L-infinity spectral convergence of the Laplace spectrometry operator, we can now move forward to say, hey, can we construct other geometric quantities of the manifold? And what interested us the most was the heat kernel, because heat kernel encodes a lot of useful intrinsic geometry of the manifold. So in this ARCHA paper, we also gave a proof showing that, hey, actually, we can also reconstruct heat kernel, and with some rate, error rate, and so on. And the purpose was motivated by doing Gaussian process regression, studying Gaussian process and the design, the coherent structure for Gaussian process, and so on the manifold and its application to medical data. So I think, for those theory, I have to say, for the previous L-infinity convergence and for this heat kernel, I have to say that convergence rates are obviously not the optimal one, and we want to improve them. So far I don't have a better idea. So if any of you has any good idea, and please, I'll be happy to talk and even collaborate and so on to get a better convergence rate, which may be better for us to understand what's really going on for the algorithm. So I want to tell you, in addition to the block-based signal, another application which is directly related to the heat kernel reconstruction. So the question is very simple. Can we do some pulmonary function test at home in the post-COVID era? So we know that digital health is getting more and more popular in our life, in particular after post-COVID. For example, we are still doing the seminar remotely and so on, although it has been, most restrictions have been lifted, and we are going back to normal teaching in person, but still people realize the needs of this digital health. So the question is very simple: how to continuously record airflow signal? For example, airflow signal, usually you have to put nasal cannula inside your nose and record the airflow so that we understand how you breathe and will you have any breathing problems, in particular for the elders and the patients with chronic obstructive pulmonary disease, COPD. What can you do? Can those people benefit from such technique? And you may ask, why don't we just put on a nasal cannula all the time? Well, you can imagine if I ask you to put this nasal cannula all the time, would you feel comfortable to go outside? Maybe the answer is no, right? So, well, there'll be some kind of thing we need to think. So the basic idea is based on basic physiology. In particular, we know that when we are breathing, our chest movement and our abdominal movement, those movement information is directly related to the airflow signal we record from the nasal directly. So why, for example, when your abdomen changes, your diaphragm will be recorded, which gives you the z-axis information of your chest or your lung capacity. And when your thoracic movement is recorded, it actually gives you the XY area information about your lung relationship or about your lung capacity. So if we can incorporate the thoracic movement and abdominal movement, probably we will be able to recover on the airflow signal. So this is a very basic idea, and turns out it works. And to make it work, and we are not really first team working on it. Like physicians have thought about it, but they use the basic linear regression ideas to do it, and so on. And we just try to improve that by introducing, by taking the nonlinear structures and into account and design a more sophisticated algorithm in this project. So for thoracic and abdominal signal, what we consider was we try to extract some useful information as covariates. For example, we apply synchro squeezing transform, which you can consider others, and I will not discuss synchro squeezing algorithm and so on. But what we can show you is after you do this feature extraction, the covariates will be located on a manifold. Okay, so that what we can do is if we view the simultaneously recorded airflow signal denoted as YT, shown on the left-hand side of the slide, okay, then could we learn the relationship in between the thoracic and abdominal movement and the airflow signal? And the relationship is written on the left bottom region, which YTI is the airflow signal recorded at time TI, and the XTI will be the covariates or features we extract from the thoracic and abdominal movement at time TI. And the F is a nonlinear function that encodes the relationship in between the thoracic and abdominal movement and your airflow. And we put some error, which we cannot quantify. And or usually you have noise inevitable. So the goal is, suppose you are a patient and at home and in a hospital, we can simultaneously record your thoracic and abdominal movement and your airflow signal, and we can label data. And then after you go home, we only record your thoracic and abdominal movement. Then could we use that information to predict your airflow signal? Or will it be possible that just use my Hau-Tieng's thoracic abdominal flow signal to train a model and apply my model to some other people that is close to me, that has physiologically close to me, and predict his or her respiratory signal? Would that be possible? That will be the question. And turns out the answer is yes. So we propose this Graph-Laplacian Gaussian process approach. Me pay attention to the time. Okay, I still have some time. Okay, so we consider Gaussian process prior as the Gaussian process, and where the m function, I still cannot use my cursor. Okay, the m, which is the expectation of f, which is the best guess of function f. Okay, and we will also have the covariance, which encodes smoothness and other properties of the deviations from n of x. And then you can get the induced covariance matrix from the data and so on. And then you calculate posterior distribution. And in this work, we just assume that we have no prior information, m is 0. And that is a basic calculation that you can get to the bottom formula by just applying some Schur's complement and so on. Okay, and what we propose in this work is how about if we take the hit kernel, or its approximation of finite sampling points as the covariance function, because hit kernel is a very intrinsic positive definite covariance function defined on the manifold. So if we can use it, then probably we will get we will get benefits. And this benefit comes from where? It comes from the fact that hit kernel captures the nonlinear structure of the manifold. For example, you have Varhan's formula to get the global geodesic distance and so on. So pictorially, you can see that suppose the manifold is on the top middle plot. That is our geometric space, which is a very simple one, only a two-dimensional space. But you can see that for the 2 points, which I cannot use my cursor, but you can see there are 2 points which are connected by the red line. That red line is the intrinsic distance. But if you forget about intrinsic distance, you forget about the geometry. You just use the ambient space distance to quantify that. Then the Euclidean distance is much smaller. Okay, and for this data, we have some ground truth response variable, which is shown on the left lower subplot. That's the ground truth. And on the top right subplot, that will be our subsampling points. And those subsampling points we have labeled. And on the bottom middle, that is if we respect the intrinsic geometry distance by using the Graph-Laplacian Gaussian process, that is what we can recover. But on the right bottom plot, which tells you if you do not respect the intrinsic geometry, then you can see some troubles. For example, there are troubles indicated by 2 small blocks. So you can see that the intrinsic geometry, respecting the intrinsic geometry is important. Otherwise, you may get something not very reasonable in the end. And a glimpse of the final results based on for this airflow recovery signal is the following. So for ABC on the top, I just showed you 3 different segments of the signals when the original airflow signal qualities vary. For example, in A, the airflow signal is good. Then you can see that the recovery is quite good. The red one is the black curve is the true signal, and the blue curve, which I have no cursor, the blue curve will be the predict mean by using our Gaussian process approach. Okay, and the gray layer is the credible interval, interval, which you can see. And on the C, that is when the airflow signal quality is not very good. It's not very good. Okay, and you can see something is kind of just crazy. It doesn't look like oscillation. And on the left bottom plot, that is just an overview of what's going on when we compared with the state of the art algorithm, which people tried. The best one was based on linear regression, locally linear regression, and so on. And we can see the improvements of the reconstruction. Okay, so now we can proceed to the second part. And the second part is scalable and the robustness, robust new algorithm. So let's have a quick look at the limitations of diffusion map. The main limitations are first, big. Okay, if data is big, then you have troubles. When the data is noisy, you may also have troubles. First, eigen decomposition is very expensive. Usually, the complexity is 2.89, so it's very slow algorithm. If you consider just take the eigen decomposition algorithm into account. So existing solutions are plenty, and the dominant two are first, how about if we consider the sparsity, right? Just make the matrix as sparse as possible using kernel and epsilon go. And problems solved. Is it really true? Well, the answer is maybe probably not that true, right? It is good if the data is clean and you can have theoretical support. But usually, neighbor searching is notoriously known to be non-robust to noise. If you have noise, you want to find your neighbors, probably the neighbors you find are not really your neighbors. Okay. The second approach will be say, hey, let's do nice strong extension, which means we do some subsampling from the big data set, and over this subsampling, we do run diffusion map and so on. And then we do extrapolation to recover everything for the whole database. It is usually good for the spectral clustering because usually you only want the top few eigenvectors. So it's good for spectral clustering. But if you want to recover the geometry, then maybe you want more. Why? Because you lose geometric information when you do subsampling. So the local geometric information may be missing in the end. So those 2 points are what we would like to improve. So our solution is the following. So we will try diffusion via landmarks. We know that in diffusion map, we want to diffuse from xi to xj. The diffusion is direct. But what about if we now try to control the diffusion via a selected subset of points called landmark set? What can we do? Right? What we do is we force xi, if you want to diffuse from xi to xj, you have to go through all x1, x2 up to all the landmarks. So you can build it as a landmark constraint diffusion. So if we consider this landmark constraint diffusion, would we gain any benefit? The answer is yes, we will gain some benefit. And we call the algorithm Roseland, which indicates robust and scalable landmark diffusion. So the algorithm is very simple, just feel nice. You can code it in your algorithm. The first step is you construct a long and a thin matrix, which describes affinities between data and landmarks, which is called WR. The second part is you try to construct the outer product of WR, which describes affinity along point data points. That is WR transpose. It will tell you the information about how you diffuse from xi to xj via all the landmarks. And you construct a D matrix, which is the affinity matrix, which is a degree matrix. And then what you do is you evaluate the singular value decomposition of D minus half WR. And why so? The motivation comes from a very simple linear algebra calculation. That is, if you want to do eigen decomposition of D inverse W, okay, then you can rewrite D inverse W in its similar form. That is D minus half WR transpose D minus half, which you can write it as D minus half WR outer product. So to do eigen decomposition of D inverse W is equivalent to run SVD for D minus half WR. And then, as usual, you multiply it back by D minus half to get the final eigenvectors. And then you can do the embedding as before. So we call it Roseland embedding with time T. So that is the algorithm. And the direct consequence of this algorithm and the benefits are the following. First, you don't need to find neighbors. You replace the neighboring information by landmarks. And there's nothing you need to search. So you get the sparsity directly. Okay. Second, the nitron extension is replaced by diffusion. And the limit of subsampling right now is replaced by using all the information via the landmark diffusion. So all data points information is used. And if you do some simple calculation of spatial complexity, you will see that Roseland algorithm is very close to nitron extension, also slightly worse, but it is much better than diffusion map, even if you consider sparsity structure. Okay, and in particular, when beta is slightly less than 1/2, you start to see that Roseland benefits and start to get faster and faster than KNN diffusion map. And for example, in this small computer, if we have a median point, p-dimensional 300, and with beta is 0.45, it only takes 3 minutes to finish it in my laptop. So even in my small laptop, I can go up to 1 million. But if you use traditional algorithm, maybe you cannot go beyond 50,000. So you get the benefit. And if you go to the larger database, cluster and so on, probably you can do better and the larger. For example, 10 to the 7 is what we are handling right now, which can be easily handled in a cluster. And I have to mention that this landmark idea, well, has been also used in the previous work. The only difference is before there was only an algorithm trying to handle images, and there was no proof, and there was no diffusion considered there. They use a different normalization. And this kind of landmark idea has been applied in many places to speed up spectral clustering. So we don't claim that we are the first group to consider the landmark idea, but to our knowledge, we are the first one trying to use the landmark to respect diffusion structure, and we prove a sequence of results. And here's a quick glimpse of the benchmark result. For example, if you take a very, very basic, old, out-of-dated database, MNIST, which has 70,000 images, then you can see that if you run diffusion map, it will take 1,000 minutes. But if you use our algorithm, Roseland only takes about 15 seconds. Okay, and we use a state-of-the-art classifier to evaluate the accuracy. And on the left-hand side, I show you that we also added some noise, and the noise is kind of not too small, and we want to see what's going on. And this is the accuracy result. You can see that when beta is 0.5, the performance of Roseland is almost equivalent to diffusion map, and it's much, much better than if you only use nitron or other algorithms. For example, this the reviewers asked us to compare. So you can see there's a dramatic difference. And even when the data is noisy, the accuracy can still go up to almost 80%, which we feel comfortable about. And this is the visualization of the whole surgery of one case. That is, we have an arterial blood pressure signal, and if we run Roseland embedding into 3-dimensional space, there are in total 120K points, and we take beta is 0.48. It only takes about 10 seconds, and this is the embedded result. So you can see that after embedding, you can see a rich structure of your hemodynamics. And sometimes you can see this kind of zigzag structure. Sometimes you can see Brownian motion structure, and so on. So it encodes a lot of information, which we can take a closer look later. So I want to give you, how much time do I have? 5 minutes?
Sure.
Okay, good. So let's, I only have a few more minutes, a few more slides. So I think I can finish everything on time. So let's take a look at the Roseland algorithm analysis. For example, the manifold setup, as you can imagine, is like before. You have a manifold, okay, and we have two random vectors. X represent the data set, Y represents the landmarks, and they are independent, okay? And we sample n points from X and m points from Y. And just like before, we assume m and the n beta, m is like on the order of n beta, and so on. And also we want to model the high dimensional colored and heterogeneous noise. So what we do is we have a clean data, manifold data, and clean landmark, and we just add something, okay? And you can see the points will go beyond leave the manifold and just spread around. And we assume that all the noise, they are independent, but they don't need to be identical. And they don't need to be white at each point. They can be colored. And the mean is 0. And we just assume that the covariance of spectral norm is bounded by sigma p. And we also assume that the p grows as n, so that p over n goes to gamma. So that's the usual high dimensional noise model. Okay, so maybe I will skip this slide or very quickly go over it. It tells you that how to choose landmark is critical, and usually we just choose landmark uniformly from a data set. But if you can design it, it will be great if you design the landmark according to your purpose. For example, if you want to recover Laplace Beltrami operator, then it will be great if you do some density estimation of the original one, and you sample the landmark according to 1 over px squared. Okay, then that will give you the effect of canceling the non-uniform sampling issue of the data set. So landmark has this nice benefit, and the design is usually a big project, big field in statistics. So I hope there are some interesting ideas there, which maybe we can borrow to improve the landmark design. But this is the field hasn't been explored yet. And we have similar L-infinity spectral convergence results. And again, it allows us to link back to spectral embedding. And I will not go into the technical assumptions here, but just we have this spectral embedding. And we also have the robustness to the colored and heterogeneous Gaussian noise, which tells you that if you get WR, which is the clean data set, and if we add tilde, that will be the affinity matrix coming from the noisy data set. Okay, and we assume that we have some constant delta p, and we fix q prime. That will be the embedded dimension. Then what we can show is if you use Roseland embedding, then the embedding of the clean data and the embedding of the noisy data, they are somehow related closely, which can be quantified using the Frobenius norm of the embedding after proper alignment, and the error is controlled by delta p divided by square root of m times n epsilon to d plus 1. And so which tells you that even if sigma p is of the order p raised to power minus 1/4 plus a, when a is any small constant, which means the noise, the total overall noise will blow up, because sigma p squared times p grows like p square root of p, which blows up quickly. Over this huge noise region, also entry-wise, the noise decreased to 0, but you can imagine the overall noise increases. Usually, when people do noise analysis, maybe the assumptions is another setup. Yeah, and we allow the noise to blow up, but still we can show that if the epsilon is chosen not too small, then you are good. You can get the stability, and that has been shown before. And the proof can actually be generalized to more general noise. For example, as long as your force moment is finite, remember force moment is enough, and then you are good. You can get the stability, and this fits our simulations, which you can find in the paper. Okay, so in the final 1 minute, I'll just go over the liver transplant clinical data. So it's collaboration with physicians, surgeons in Taipei Veterans General Hospital, which was my training hospital back in my medical physician life. And they're all my collaborators. They collected 60 cases within some years. Okay, and you can see a lot of different geometric structures in the Roseland embedding. For example, over this part, it is like a Brownian motion. Over this part, it's like zigzag. So we consider some clinical indices that physicians could easily accept and apply. One we call trend, one we call fluctuation. And we can see that the trend information provides useful prediction power before your wound is closed during the surgery for the outcome 8 days later after the surgery. Here, the total bilirubin, TB means total bilirubin, and the DB means direct bilirubin. Those are two indices physicians look at to evaluate if the liver transplant is good, or if there's any big trouble in the liver transplant, because it tells us if the biliary duct is any troubles or anything. Okay, so we may suggest if the ultimate goal is everything under development. Ultimate goal is during the surgery, we will tell the physician, hey, you may want to take a second look. There may be some problems in your surgery before you close the wound. And if he can do this, then maybe the patient will be saved. Otherwise, if there was a failure, then the patient has to suffer again, and which is usually not very good. And certainly, we need a larger database and more collaboration to proceed with this direction. There are several summaries. For example, it provides a novel and integrated general framework that enable an early intervention. Okay, find hidden details in nonstationary time series, which is not detectable by human eyes, and it can be applied to other data sets and so on. So that is my talk today. Thank you for your attention.
All right, let's thank the speaker with clicking the reaction button.